Hey everyone, Mr. Caldwell here. Wanted to talk a little bit about electric fields with you for just a moment. Electric fields are a pretty convenient way of visualizing what's going to happen to a tiny little positive charge if we bring that tiny little positive charge, and we call it a test charge. We bring that tiny little positive charge near other charges. Now, if we go back and think, well, we know that like charges repel and unlike charges attract. This field stuff hopefully isn't too scary. So we'll come back to this little simulator first, but I'm going to start over here. And there's a couple of key points when we're talking about electric fields. So I'm going to put a positive 1 nanocoulomb. So a nanocoulomb, nano is just a prefix. It's a pretty small prefix. So it's not a very large amount of charge. And what you'll notice is that you have these lines that are pointed away from the positive charge. And that's a key point. Electric field lines always point away from positively charged objects. If I were to put a negatively charged object, since they point away from a positive, guess which way they point? They point towards a negative, right? So, and remember what I said at the beginning. What these lines, what these arrows represent is the direction that a small positive charge would feel a force in. Well, if I bring this little yellow sensor, that's my little test positive charge. Well, isn't it going to be attracted? A positive would be attracted to a negative. So we see a little red arrow here. And depending on where I put my little test charge, notice how the arrow always lines up with all those white arrows on the screen. The white arrows represent the field lines, all right? They are representing which direction this little test charge would feel a force. So remember that arrows point away from a positive charge and towards a negative. So what we'll do is we'll clear this out, and we're going to put a positive test charge here and a negative test charge here. And what we end up with is kind of a cool little shape. We get these curvy lines, right? And again, remember, all of these lines represent is the direction that your positive test charge would feel a force at. So at this location right here, all right, there's some repulsion between this positive and our little positive test charge. So that's wanting to push it away this way. But because it's a little bit closer to the negative, there would also be a fairly strong pull towards the negative. So when you combine a repulsion in this direction with an attraction that's a bit larger in this direction, you get sort of a splitting of the difference. You get a little bit of a pull off in this direction. So again, the field lines just represent the direction in which a positive test charge would feel a force. And I think in another video, we talked about how to calculate that force using Coulomb's law, F equals K, absolute value of Q1 times absolute value of Q2 divided by distance squared. Now, here's the other thing that you need to realize about electric field lines. All right, so I'm going to start with a little bit of a different simulator here. So right now I've got two dots that have no charge whatsoever. And what I'm going to do is I'm going to slowly increase the amount of charge here. All right, you'll notice that the arrows might be a little hard to see on your screen, but there are arrowheads that are pointing outward away from this positive charge, which is a charge of +1. Units not given. But notice what happens when I change it to a charge that is slightly larger, right? You should have seen an increase in the number of field lines, okay? And if we were really being ticky-tacky here, I wonder if it's actually a doubling of the field lines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 field lines here. And now I'm at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Wow, that's really nice. It's actually showing exactly what it should. A doubling of the charge caused a doubling of the number of lines. All right. So we can see that by looking at sort of the density, the intensity, the number of lines that we see gives us a rough indication of how strong the charge is. So this is a really positive charge here, and everything would be, these little positive test charges would be just flying away. Now we've left this guy all alone over here. So let's back this down to a reasonable charge of 1. Let's make this a -1. Well, we know that the arrows have to point towards the negatives. So what we get is this sort of closing of the loops, right? And remember that these are just showing the direction that any little positive test charge would feel a force if it was located at any of the individual positions on this sort of map. And so we can increase the amount of negativity, so we get more and more lines coming into the negative, and it changes the look of our field lines, right? So that's when there's a positive and a negative. What if we had 2 of the same charge, right? So let's say that we had a +3 over here, just like we have, and let's make this -3 into a +3. Remember that the arrows always point which way? They point away from a positive charge. So you get this kind of interesting thing going on. The lines that are pointed away from this guy run into the lines that are pointing away from this guy, which leads us to sort of the last important idea with field lines. So we had idea number 1, they're always away from positive and towards a negative. All right. Number 2, the number of lines directly relates to the intensity of the charge. More charge, more field lines. And then rule 3, field lines can never cross one another. All right. You'll notice that these lines, they approach each other and then they just go away from each other because they can't cross. All right. So if we were to put our little positive test charge somewhere in this region, kind of makes sense that he's going to zip right away here because he's going to be repelled from this positive and repelled from this positive. We'd see a similar thing here with negative charges. The only difference is the direction of the arrows, right? Because remember that the arrows point in towards a negatively charged object. So I'm hoping that this little review of electric fields and electric field lines helps you, all right? And if you can remember those 3 key rules: away from positive towards a negative, right? The number of field lines is directly related to the intensity of the charge, more field lines, and field lines never cross. All right, hope you're well, and I'll catch up with you soon here. Take care.